All right, our next speaker is Maelia Gomez. Maelia works at Astrea Separations. Some of you may know it as Prometic. That was the name they used to be, at least when I was a grad student. Prometic is doing some interesting work on synthetic ligands for antibody purification, and Maelia has extensive knowledge in implementing novel chromatographic techniques for the purification of monoclonal antibodies and optimizing chromatographic processes to increase product yield and purity. And that's actually the topic of our presentation today. So, Maelia, we look forward to your presentation. The floor is yours.
Thank you for that. Hi, my name is Maelia Gomez. As mentioned, I'm a field application scientist with Astrea Bioseparations, and today I'm going to be talking to you all about some of the work that our wonderful R&D team has done. To address some issues with FC lacking antibodies as well as novel antibody formats. So that's what we're going to be talking about today. So as we look at the evolution of antibody therapeutics, one thing is quite clear. The diversity of formats are evolving quite rapidly. Traditionally, monoclonal IgGs have dominated the landscape, but in recent years we've seen a sharp rise in more complex structures such as bispecifics, ADCs, multispecifics, and immunoconjugates, as illustrated in the chart here. Since 2010, there's been consistent growth in first approvals, and in just the past 5 years, the proportion of engineered antibody formats has grown quite dramatically. But the question is, why does this matter for downstream processing? And that's because each new format brings structural and biophysical challenges that impact how it purifies, whether it aggregates its tendency to form mispaired chains or binding behavior to chromatography resins. And that's the key message here today, that antibody purification can no longer rely on a one-size-fits-all workflow, but rather we need tailored format-appropriate solutions for these sort of novel antibody formats. And that's exactly where Astrea Bioseparations focuses their innovation. So antibody purification isn't straightforward, and that's because every molecule behaves differently. Each format varies in size, charge, stability, and how it interacts with purification resins. On top of that, the expression system can add more complexity and a different impurity profile. For mAbs, this process is pretty well established, and protein A has been the industry go-to for decades. And for traditional IgGs, it does still work quite well. But as antibody engineering evolves, so do the limitations of that sort of standard approach. Many next-gen constructs, including fragments and certain bispecifics, lack the FC region that protein A relies on. And without this FC region, a shift in strategy kind of starts right at the beginning of the process. But the challenges, they don't stop there. Newer antibody architectures often come with added structural complexity, like chain mispairing in bispecifics, or a higher risk of aggregation. These issues make polishing much more difficult, especially when trying to maintain high yield and product quality. On top of that, these molecules can behave quite unpredictably when it comes to impurity clearance. Things like host cell proteins, DNA, and endotoxins may persist through your standard polishing steps and require more tailored solutions. The schematic here gives you sort of a sense of that structural diversity, from full-length IgGs to fragments, bispecific T-cell engagers, and cross-mAbs. And that sort of brings us back to our key message for the day, which is that as these formats diversify, so must our purification strategies. Ultimately, there is no single purification strategy that works for all formats, and you really do have to tailor the approach based on the molecule's unique characteristics. So when purification gets tricky, whether you're dealing with mAbs, fragments, bispecifics, or other engineered formats, we believe the answer lies in flexibility. Our downstream purification toolbox is built around two core areas, capture and polishing, with format-specific solutions spanning mixed-mode resins, ion exchangers, and HIC, and more. For example, if you're working with fragments, we offer PuraBead HX2. This is a synthetic ligand designed specifically for FC-lacking constructs. For things like bispecifics and multispecifics, we have SP PuraBead Edge on our fast flow 65-micron bead. This offers the performance resolution needed to compete with small bead alternatives without sacrificing flow rate or pressure limits. Our mixed mode resins bring added versatility to the toolbox, helping to navigate purification challenges that aren't as easily addressed by traditional ion exchangers or HIC resins alone. These operate in pretty unique spaces compared to other market alternatives. And the great thing about this is that all of it is super scalable. We support screening with robo-columns and high-throughput prepacks, and up to our SNAP column range for things like viral clearance studies, and Evolve columns for GMP manufacturing. The goal that we have here is really simple. We're looking for total flexibility and not forcing your molecule into a predefined process, but rather building a workflow that works for your specific format, backed by the right tools needed at each development stage. So if you're working with a challenging antibody, this toolbox is really built to help you. And now I'm going to go into a couple of case studies to highlight a couple of our resins and show you their use in real-life applications. So first, introducing PuraBead HX2. This is our mixed mode capture resin for FC-lacking constructs. Typically, protein L is used for light chain capture, but it does have its limitations in its selectivity and caustic stability, and that's where PuraBead HX2 comes in. It is a caustic stable mixed mode resin with affinity for both lambda and kappa light chains. It's also now available in our new 96 well plate format and can be scaled up to GMP. First, we're going to go over a case study that highlights the competitive performance of PuraBead HX2 for an E. coli-derived VK protein. So first, a DOE screen for load optimization was performed to determine the optimum load conditions for PuraBead HX2. This was a full factorial design to assess the impact of salt and pH on binding capacity, recovery, and purity. The operating window assessed for this DOE was a pH ranging from 7 to 10, and salt concentrations from 0 to half molar, as we can see on the heat maps with pH on the x-axis and salt concentration on the y. From this screen, it was determined that the performance was optimized at high pH and low salt concentrations, also as seen on the heat maps in the red area. And the table on the bottom shows the results from confirming the load conditions of tris at pH 9, so high pH, low salt, on a 1 ml pre-packed column. Results were comparable to the screen as the team had expected, and the team was able to achieve 15 mg per ml of adsorbent load density, and about 80% of the VK protein recovered in the elution, with a purity of greater than 80%, which translated to a purity improvement of over 4-fold. After load optimization, the team worked on optimizing elution conditions. So different buffer systems were assessed under the determined optimized load conditions. Buffers used were citrate, McIlvaine's, and acetate all over a respective pH gradient to their pKa's. All of the pH gradients were able to effectively separate the VK fragments from the non-target proteins, with the VK fragments eluting at a higher pH. Elution assessment was run on a 1 ml pre-packed column, similar to the load assessment. And the chromatograms for each buffer system are shown at the top. These chromatograms are zoomed into the pre-elution, elution, and strip steps if performed. And looking at the gel image on the bottom, we can see the recovery of the VK fragment from each elution buffer, along with the, again, strip if it was performed for that step. We can see that the citrate and McIlvaine's gradient showed a more gradual recovery of the VK fragments over their respective pH gradients, while most material eluted during the acetate pH 5.5 pre-elution wash. Of the 3 buffer systems tested, they all achieved high VK purity of about 98 to 100%. But in terms of recovery and host cell impurity clearance, acetate beat out citrate and McIlvaine's buffers. Specifically, an acetate elution at pH 5.5 was able to achieve, was able to achieve 3.5 log HCP clearance. At this pH, citrate and McIlvaine's buffers struggled to clear 1.5 log. This means that with the acetate elution, the material is cleaner and places less of a burden on further polishing steps. The citrate and McIlvaine's buffers also required an additional pH 4 elution step to match the recovery of the acetate elution at pH 5.5. A milder elution with acetate helps us maintain product integrity and reduces the risk of aggregation at low pH. For this purpose, the optimal elution buffer for MyMode PuraBead HX2 was acetate at pH 5.5 for a high purity VK elution. The optimized run conditions were then sort of put to the test to compare MyMode PuraBead HX2 to a competitor protein L resin. For this comparison, MyMode PuraBead HX2 was loaded at pH 9 and eluted with acetate at pH 5. Recovery was comparable between both resins with about 77 to 78% VK yield. However, the difference is really in the purity of the eluted material. So MyMode PuraBead HX2 was able to achieve 3.67 log reduction of HCP versus the 1.84 log achieved with Protein L. Additionally, the milder elution conditions reduce the risk of denaturation or aggregation at low pH that you might see with the lower pH elution with Protein L. This is important because, sort of as mentioned in the previous slide, the cleaner your material is going into your downstream polishing steps, the less of a burden there is on those polishing steps to remove process and product-related impurities. We also ran this side by side through a cost efficiency model, and so not only did MyMode PuraBead HX2 demonstrate comparable technical performance, it also delivered meaningful cost savings per gram of biologic produced. So to recap, MyMode PuraBead HX2 is our purpose-built solution for capturing FC-free antibodies that can't be purified using traditional protein A. It's a mixed-mode resin, as mentioned, but what really sets it apart is its synthetic ligand. It's designed to specifically target both kappa and lambda light chains, giving it a pretty broad compatibility with a wide range of FC-lacking constructs. The synthetic nature of the ligand also gives it really great base stability. It can stand up to 1 molar sodium hydroxide during clean in place and can support over 200 reuse cycles. That means consistent performance across runs and excellent lifetime value. Compared to market-leading protein L, MyMode PuraBead HX2 offers lower resin cost, similar recovery, and higher purity, translating to meaningful cost efficiency and better process economics overall. Operationally, it's also easier to work with. There's no cold storage needed, and it's compatible with your standard LCMS workflows. And again, as mentioned, it is now available in our 96-well plate format for your screening needs and purposes. Moving on to polishing, SP PuraBead Edge is our next generation strong cation exchange resin, specifically designed to meet the growing demands of high throughput, high resolution downstream polishing. It's built on our Agarose 65 micron base matrix, giving you the ideal balance of resolution and flow. This means that you can maintain performance even at fast flow rates, which is really critical when you're trying to improve productivity without sacrificing separation. This makes it especially powerful for things like bispecific antibodies, which often present with mispaired chains and aggregate species that need to be resolved cleanly, which we've highlighted in a case study to follow. SP PuraBead Edge is also designed for scalability. It performs consistently across formats, flow rates, and residence times, making it a strong candidate for platform processes that need to move from development to GMP scale without the need to re-optimize everything. So whether you're focused on monoclonals, bispecifics, or even more complex modalities, SP PuraBead Edge gives you a tunable and high-resolution polishing tool that fits seamlessly into your bioprocess workflows. So first, let's take a look at a comparison of SP PuraBead Edge to 2 commercially available cation exchange resins of different particle sizes. So as a reminder, SP PuraBead Edge is on our 65 micron bead, and we compared it to a 90 micron and a 34 micron bead. In this comparison, we assessed dynamic binding capacity across different residence times. Importantly, SP PuraBead Edge showed superior flow properties versus competitor resins. The competitor 90 micron resin lost performance at the faster flow rates, and the 34 micron resin couldn't even operate at the 1.5 minute residence time due to excessive back pressure. Our SP PuraBead Edge handled both with ease, making it an ideal solution for high throughput and scalable workflows. Against those same 2 commercially available resins, we wanted to assess resolution at varying residence times. A standard protein mix of lysozyme, alpha-chymotrypsinogen A, and cytochrome C was loaded to 10% of each respective resin's binding capacity. SP PuraBead Edge, as we can see in the graphs, was able to fully resolve peaks 2 and 3 at all residence times, but fell just short of the threshold for full resolution for peaks 1 and 2. It was able to resolve them at the 4 minutes, but as mentioned, just fell just below the threshold for the faster times. While the 34 micron resin was able to resolve all peaks, again, it was unable to operate at a residence time below 2 minutes due to excessive back pressure. And as for the 90 micron resin, it failed to resolve any peaks at the higher flow rates. However, again, SP PuraBead Edge was able to offer superior peak resolution and consistent performance across various flow conditions, making it an ideal solution for your high-resolution needs. The next case study demonstrates the performance of SP PuraBead Edge as a polishing resin for bispecific antibodies. This is a format known for its structural complexity, mispaired chains, and tendency to aggregate post-protein A. The model used was a CHO-derived bispecific with a molecular weight of 125 kilodaltons, composed of a kappa light chain, IgG heavy chain, and chimeric single chain variable fragment heavy lambda chain. Some of the unwanted isoforms include a sort of higher molecular weight, 150 kilodalton, kappa plus IgG heavy chain homodimer, and then a lower molecular weight impurity of 100 kilodaltons of the single chain variable fragment homodimer. For this case study, protein A was used as a capture step. The protein A eluate was then intentionally stressed and held at pH 9 overnight before adjustment to pH 5 to stimulate high aggregate conditions. This material was then polished with SP PuraBead edge with the goal of removing aggregates and resolving mispaired isoforms. Experiments were performed on a 20 centimeter bed height column, and the column was equilibrated with sodium acetate at pH 5 and eluted over a 0 to 50% gradient of 1 molar salt in sodium acetate at pH 5.6. Initially, a 40 CV gradient was run to provide a baseline resolution. Then this was optimized and cut down to 20 CVs in order to reduce runtime. And finally, a stepwise solution was implemented for enhanced resolution of the isoforms and aggregates. So first, 46 mg of the protein A purified bispecific feed was loaded onto the 3.9 mil column packed with SP PuraBead edge. The initial 40 CV gradient resolved 4 distinct peaks seen in the chromatogram on the bottom. From the gel image, we can see that a majority of our target protein was recovered in elution peak 3, with high molecular weight aggregates eluting in the earlier fractions. Crucially, it enabled clear separation of mispaired chains from the bispecific product, and this is a key step in overcoming one of the most persistent challenges in bispecific antibody manufacturing, which is product heterogeneity. That brings us to our optimized gradient over 20 CVs in order to decrease the runtime while hoping to achieve comparable resolution to the extended gradient. As shown by the chromatogram, SP PuraBead edge was still able to resolve the 4 peaks, achieving separation of the target bispecific antibody in peak 3 from mispaired chains and aggregates. Even over a condensed gradient, SP PuraBead edge was able to achieve efficient resolution of the target bispecific antibody and impurities while improving process throughput. Finally, we implemented a stepwise elution to enhance resolution and improve process efficiency. In this instance, the resin performed exceptionally well. It reduced aggregate content from about 20% to under 5%, and this time it resolved 6 distinct species. The bispecific antibody was eluted at about 28 millisiemens per centimeter, with high molecular weight impurities eluting in the later fractions. We can see that potential mispaired species eluted in some of the earlier fractions around 16 and 22 millisiemens per centimeter. Overall, though, this isn't just about resolution. It's about reliable, tunable performance that can hold up under pressure and position SP PuraBead edge as a commercially viable platform polishing solution for even the most difficult to purify bispecifics. At the heart of our antibody toolbox is the PuraBead base matrix. This is the platform that powers the performance across our full suite of chromatography resins. PuraBead is an advanced agarose base matrix engineered in-house to support a range of pore sizes and particle diameters, giving us the flexibility to tailor solutions from capture to impurity removal. Across all these applications, PuraBead delivers high mechanical stability, tight particle size control, and low back pressure, enabling robust, high-efficiency separations even at scale. PuraBead is made from agarose, sourced from renewable, sustainably harvested red seaweed, which contributes to ocean health and captures CO2 through photosynthesis. The seaweed is then solar dried and transformed into agarose beads via a fully aqueous and solvent-free manufacturing process. This eliminates hazardous solvents and significantly reduces waste and emissions. The final product is also biodegradable and can support hundreds of CIP cycles, delivering long-term durability while minimizing waste, replacement frequency, and overall cost per batch. And because Astrea Bioseparations controls the entire production process from raw materials through to ligand coupling, we offer not only performance, but supply chain control, quality consistency, and faster response times when market conditions shift. So as we start to wrap up, it's worth stepping back to look at what really sets Astrea Bioseparations apart. We bring over 30 years of experience in bioprocessing, and this is a track record built on trust, innovation, and proven performance. Our expertise spans the full spectrum of bioseparation products and services, from capture to polishing, and from standard formats to highly customized solutions. Our products are manufactured in cleanroom facilities under ISO-certified conditions, and we back that with comprehensive regulatory support to streamline your path to GMP adoption. Today, our technologies are used in 21 FDA-licensed products, and that number continues to grow. So to recap, antibodies are evolving, and purification needs to evolve with them. From FC-free fragments to bispecifics and more, Astrea's antibody toolbox gives you the flexibility, performance, and control to meet today's purification challenges head-on. We've shown you how MyMode PuraBead HX2 and SP PuraBead Edge play a role in tailoring downstream workflows, all powered by our sustainable, high-performance PuraBead base matrix. These can be packed in any of our column format range, as shown earlier, from the small scale up into our Evolve for GMP manufacturing. So if you're looking for help with a complex target, you want to explore custom ligand attachment, or just want to see what smarter purification looks like, you could come speak to us. We are downstairs at booth 625, and we'd love to hear about your challenges and see how Astrea can support you. So thank you for your time, and we look forward to connecting with you soon.
Thank you, Maelia. Thank you, Maelia. Any questions for Maelia? Any questions, any questions, any questions? I do have a curiosity. So the protein L mimetic ligand is a triazine scaffold?
Yes.
If I caught you correctly, after elution, there was a significant quantity of Fab that was found in the stripping, in the resin regeneration. Mm-hmm. And they both seemed to have comparable purity. Mm-hmm. Now, I can see how two potential proteoforms of Fab would come out at different times on a elution gradient in an ion exchange, but in an affinity setting, yeah. I was wondering whether you know what causes so much Fab to bind so strongly and be present in the strip, in the resin strip.
Yeah. Again, so MyMode PuraBead HX2 is a mixed mode resin and not a pure affinity resin. And so it's hydrophobic and hydrogen bonding are the two sort of modalities that make up the mixed mode. And so we're thinking that it just has to do with the hydrophobicity and the conditions, on the column at the time.
So it's still conceivable that the protein would come out at different time points, depending on how it binds mm-hmm. with the ligand. Makes sense.
Hi, I had a question regarding the PuraBead CX resin. I think you showed data that showed that you were essentially getting independent DBC with respect to flow rate with that resin. Is there something about this resin that's allowing for improved mass transfer that's allowing you to achieve those consistent DBCs?
We're thinking it's, well, obviously the smaller particle size is helping with the increased DBC over other resins. But in terms of why it's consistently across the board, we're thinking it's in our base matrix. It has a really tight size distribution, and so we have a really, all of the bead sizes are very similar in size, and so that really helps us with consistency across the board because our base matrix is so consistent.
As a follow-up to that question, what about pore size and pore size distribution? I might kill myself here.
So depending on the bead, for our 90s and for our 65s, I think the tolerance is plus or minus 10 microns. So it's a pretty tight size distribution, yeah.
Nice. Oh, sorry, yes.
Hi. Can you speak to the dynamic binding capacity of the protein L resin?
Of MyMode PuraBead HX2, our alternative, I would have to look back. I know that in the dynamic binding capacity study that they did, they were able to achieve up to 15 mg per mil of the Fab. It does have different binding capacities for different antibody formats, so we've seen that it can change based on the antibody format that you're using. But for Fabs, we've seen around 15 mg per mil of absorbent.
If there is one, we can perhaps take one more question. Going once, going twice. If not, please join me in thanking Maelia again and the other speakers for this morning's session.
Thank you.